Hello, everyone. I'm Corey Mitchell, and I'm presenting with Sebastian Berrigan, Alex Fung, Zachary Richter, and William Henriksen. And our topic is on Bang Bang spacecraft attitude control thrusters. And the image on the right is one of the quad thruster blocks on the Apollo service module. All right, so Bang Bang thrusters are reaction type actuators for controlling spacecraft attitude, and they're different than momentum type devices like reaction wheels because angular momentum is not conserved since an external force is applied. And Bang Bang thrusters are generally used when the desired torque is greater than what can be put out from a reaction wheel. And by nature, they just put out a constant thrust and therefore constant torque. So they go from a zero thrust level to 100%. And they're pretty much the simplest form of propulsion where, as shown on the right, all you really have is pressurized gas separated from a nozzle by a valve. And ideally, this valve would open in 0 delta time, but realistically, that really can't happen for actual systems. There's some hysteresis, there's some lag between 0 level and 100%. And the whole goal is to just control the pointing attitude of a spacecraft rather than the orbital translation in position. So the figure on the lower right is a little bit misleading because to only control the attitude, you would need a second thruster on the lower left to cancel out the horizontal force. Since there are only two possible states in a Bang Bang control scheme, either completely on or off, it lends itself well to rest-to-rest maneuvers in space. The simplest strategy is to mathematically find the time to switch between acceleration and deceleration to get to another attitude as fast as possible. In an actual Bang Bang control scheme, an ideal rest-to-rest maneuver is based only on the sign of the error rather than its magnitude. As shown in equation 1 on the right, the error in this case is just the linear combination of the pointing orientation and angular velocity of the spacecraft. This equation doesn't specify the width of the thrust impulse, it just specifies that if you exceed the error in one direction, apply thrust torque in the other direction.
Pulse width modulation, commonly referred to as PWM, is used to create a more continuous torque profile and can be implemented with various different methods. Schmitt triggers, in combination with other common circuits, including filters and comparators, can create analog pulse modulated signals. The signals can also be generated digitally with algorithms implemented in the system's software or firmware. By changing the duration that the thruster is firing for during a cycle, we can change the effective continuous torque acting on the spacecraft. The figure on the right shows an example of this. The solid line, labeled T sub C, is a continuous torque signal calculated from the control algorithm that has been discretized with a zero-order hold device. The dashed line, T sub T, shows the PWM signal of the firing thruster. For lower required torques, it is clearly seen that the thruster is firing for a smaller percentage of the cycle, while higher torques result in longer thrust durations. It is important to note that in this example, the discretization and PWM cycle duration is the same. Depending on the system's characteristics and constraints on the thruster's firing times, it could be possible to have multiple pulses, or PWM cycles, in a single discretization period. Since a thruster can only generate force in one direction, it can only produce a positive or negative torque about some axis. Therefore, at least two thrusters are required to produce a multidirectional torque about an axis. To be able to completely control the attitude of a spacecraft, the thrusters must be able to generate torque in either direction about 3 spatial axes of the spacecraft. This results in a minimum of 6 total thrusters for any given spacecraft. Many spacecraft will utilize more than the minimum number. 12 is commonly chosen, and the thrusters are fired in pairs such that the torque is generated by a force couple, which causes zero net force on the spacecraft. This creates pure torque about the desired axis and does not affect the orbital trajectory of the spacecraft.
Bang Bang thrusters produce discrete changes in angular velocity. This is due to the thrusters firing a constant thrust over a discrete amount of time. Bang Bang control is optimal in theory because it minimizes the time. However, it is not in the real world because there is error. We don't get exactly to the desired attitude. When we get really close, we need to make a small adjustment, but bang-bang thrusters are very bad at making tiny adjustments. This is because we would want the motors to fire at a very small time, which would be less than the minimum time the motor is physically capable of firing. This physical limitation is due to the valve opening and closing. The result is an overcorrection after an overcorrection, and it appears as an oscillation around the target attitude. This is also called chatter. And that parameter is called the minimum torque impulse bit, which is just the minimum time the thruster can fire for, multiplied by the magnitude of the torque it produces. To make them more continuous, we can fire more often for less amounts of time to get equivalent control. However, we change the length of time as we get closer to the desired attitude. We start with longer bursts and then shorten them up as we get closer to our target attitude. This reduces the error as we get closer, and it results in a much closer oscillation around the desired attitude. This high frequency on-off signal results in a continuous behavior very close to that desired attitude, and we can linearize it when it's high frequency by using average thrust values.
Now the question is, how do we deal with thruster layout and redundancy? Well, thrusters should be laid out around the spacecraft in positions as far and normal to the center of mass as possible for maximum mechanical advantage to increase the fuel efficiency of the spacecraft. The most common layouts are symmetrical about the axes of interest, and thus result in even numbers of bang-bang thrusters. The historical method for redundancy measures is to maintain a 1-to-1 ratio between active and inactive redundant thrusters, so if one fails, another can replace it. Newer satellites, though, are beginning to employ fewer redundant thrusters because the cost of launch has decreased so significantly that sending an upgraded version of the satellite may be better in the long run. Thrusters are selected for firing through onboard sensors that determine the attitude and send it to the onboard computer for processing. The onboard computer processes this autonomously through an algorithm that employs a control feedback loop to determine the required correctional torques. On the right, you'll see an image, which is a high-level diagram showing this process. After the required torques are determined, the thrusters are then fired, and the entire process happens very rapidly. Here's an example of SpaceX testing their bang-bang thrusters for the Dragon capsule. And now you'll see more examples of modern day spacecraft using bang-bang thrusters.
We've now seen a real-life example of a propulsion module firing using bang-bang thrusters, and we will now discuss other modern examples. NASA's Orion spacecraft is a human spacecraft designed for deep space missions to the Moon and Mars. It had its maiden voyage, Exploration Test Flight 1 in 2014, and it proved a success. It is controlled by pulse-width modulation controllers that will help guide the spacecraft to its far-reaching destinations. NASA's Ares 1 is another example. It is a crew launch vehicle to be used to launch other spacecraft, where the roll of the rocket is controlled by non-linear bang-bang thrusters. And in figure 9, you can see the Orion spacecraft, and in figure 10, you can see the Ares 1 during its test launch. In summary, bang-bang control thrusters are used when momentum thrusters are insufficient, and when you want to utilize constant thrust and constant torque in your spacecraft. Bang-bang thrusters are theoretically optimal, but practically insufficient compared to other propulsion methods. However, pulse-width modulation can be used to help fix the problems with a pure bang-bang system. Bang-bang control utilizes 6 minimum thrusters to control the 3 axes, but There are typically 12 present on a spacecraft due to attitude control maneuvers. And there are plenty examples of bang-bang thrusters being implemented in modern missions with modifications.